construction indeed exists for gravity. Okay, so now let me move on to the third conjecture for black hole information. So let's imagine that we make a black hole collapsing some classical matter. It forms and then evaporates. And it evaporates at the Hawking temperature, 1 over 8 pi gm. And the number distribution of the quanta of energy omega of a Boltzmann distribution, omega squared over this factor. And this distribution goes to 0 as omega goes to 0. Simply doesn't have a pole. So this distribution, we can think of these all as hard quanta. We aren't producing copious numbers of soft quanta, and they're hard where the hard energy scale is 1 over the length of the radius of the black hole. Now, Hawking proposed in 1975 that this in-state coming in here will evolve to a mixed state, which where we have a sum over all hard states. I don't want to get into too much detail about what these are, but they're essentially the states that you would get from a black body radiating at this temperature for some time until it disappears, and with some probabilities that are essentially thermal probability distribution functions. Now, a few years later, 5 years later, John Page came along and said, I don't like that. I want information to be, I want unitarity, I want information to be preserved. And so I'm going to conjecture that instead what happens is the in-state goes to some pure out state where the C alphas would depend on the details of what was thrown in, and the H alphas are some typical element of a hard state consisting of hard quantita that appears in the probabilistic calculation that Stephen did. And moreover, the quantum purity, and we heard a little bit about this in Douglas's talk, the quantum purity is restored, if we were to look at such an evaporation process, by correlations between the hard quanta which emerge at early times and the hard quanta which emerge at late times. In other words, for the first half of the evaporation process, everything looks thermal, but in the second half, the quanta which come out somehow know about the quanta that came in, and the whole thing is a pure state. This is impossible. It's impossible for the same reason that this can't happen, because it violates the conservation law. It's impossible for the same reason that E plus E minus cannot scatter to E plus E minus. We must have soft quanta produced in any kind of evaporation process like this. So I'm going to propose an alternative to Page's conjecture, in which the in-state goes into an out-state, where we have also this hard, which is a sum of five states, where every hard state is appropriately dressed with some soft quanta. So Don didn't give any prescription or algorithm for how you compute these C's. He didn't say firewall or football or whatever. He just said there should be some mechanism so that it's happening. And similarly, I'm not proposing any prescription here. I'm just putting this forth as an alternative to what Page was saying. And now I'm making a second conjecture that the soft states are orthogonal. That is, that the soft state associated with any hard state is unique. And if you do that, if you look at an inclusive cross-section, if you detector that can't observe the soft quanta, you must trace over the soft state. And then you get back exactly the Hawking formula if this C alpha is equal to the square root of Stephen's rho alpha up to a phase. So in this correlation, so in this conjecture, a person equipped with a detector that cannot see the soft quanta will think that Stephen got it exactly right. And in order to see that there is a unitary evaporation process, one will need to measure the soft quanta. So this is a kind of minimal deviation, which is consistent with unitarity, but is very close to what Stephen was originally proposing. And the quantum purity here is restored not by late and early hard quanta, but by hard quanta and soft quanta. Now, could it be true that these S's are orthogonal? I think I won't go through the argument here. I won't go through the details of this argument, but I looked at it in a theory of in which all the initial and final quanta are gravitons, and using supertranslation charge conservation, which is, so in electromagnetism we have all these charge conservation laws from the matching of the radial component of the electric field. In gravity, we have analogous infinity of conservation laws from the matching of the mass aspect. That is supertranslation charge conservation. And then we have a second infinity from the matching of the angular momentum mass aspect. That is superrotation charge conservation. And you need both of those to decohere, to fully decohere, for the soft quanta to fully decohere the hard gravitons, and then in that case tracing over the soft quanta fully decoheres the hard ones. And a very similar conclusion was reached in a beautiful paper last week by Terry, Carney, and Siminoff, and other a few other people, in which they looked at a generic scattering process and showed that in a generic scattering process of hard particles, even in electromagnetism, you greatly decohere the S matrix element when you trace over the soft quanta which are produced. Now, I want to say again that I'm not giving an algorithm here for computing what the C's are. Computing what the C's are, so to solve the information puzzle, maybe you don't have to give a number for all the C's, but you have to understand how to compute them in principle. Like for burning lump of coal, we could imagine how we could put it on a computer and compute the radiation exactly. Here we don't have a proposal, a dynamical proposal for computing what all the C's are. But this picture fits in beautifully with the work I've been doing on self-care with Stephen and Malcolm. And so we'll have to go into the details of the evaporation process, understand more what the implications of how a black hole carries these charges, what the implications of that are for the evaporation process, and that Enterprise is in process as we speak. So in conclusion, we've over the last 30 years we've saw a lot about ultraviolet of quantum gravity, and there's all kinds of fantastic, beautiful things, interesting things that can happen in ultraviolet of quantum gravity. But also the infrared of quantum gravity is extremely rich, much richer than we once thought, and has already yielded some surprises in the last few years, and we are hoping for more. Thank you very much. When you last came to visit us, at least when I was here, you gave a beautiful colloquium and it mainly focused on the QED case on the electromagnetic case. Put me in mind of remarks of Roger Penrose, which geometrized what you said, I think, and that is the following. Really, if you're looking at the conformal group on the conformal impact time cross space, you should identify strike plus and strike minus. And that's very clear for various symmetrical constructions. And that means, since it's not simply connected, that you have non-trivial bundles. You have to, in the field of sections of non-trivial bundles, which is precisely your antipital map transformation. And moreover, because it's not simply connected, you have flat connections with non-trivial polynomial, and that seems to be very much how you're describing the charges. So I think I like the S-matrix, I should say, partly because we used to go for here and just get in, but it seems to me that there could be a different way of formulating these problems for certainly electromagnetism, and I suspect also Yang-Mills, certainly pure Yang-Mills and pure electromagnetism, which would somehow eliminate even the mention, this is the behavior system point, you would not even mention the S-matrix yourself concept. You'd be dealing with a regular field theory on a compact space with peculiar identifications. And I believe that's solely because if you ask people about behavior system and how they prove Yang-Mills classically exists, they lift it onto precisely the same space. They have a compact cross-section, and so they can use all their theorems of functional analysis. So it may be that this picture that Roger gave us in this particular case, Roger's aware of this is what is still in the trade, the Gödel discontinuity. But maybe we shouldn't focus on strike plus and strike minus as separate things in this particular case, but rather the same place. Yes, and there are many different directions and ways that one could go with that comment. But I do one thing that is, I'm just talking about one little corner here, but there is a picture which seems to be a very nice one, which is exactly what you want, which is to get rid of strike plus and strike minus and just keep the sphere, the celestial sphere, and then the scattering is a kind of correlation function on that sphere, and that is the sphere. That is the most natural way to think of superrotations and how they act. But certainly, yes, Penrose did. I've had in the course of this investigation reasons to read some very old papers of Penrose, and it's amazing some of the things he knew a very long time ago. But he got some things wrong too, and I think the conformal compactification was too strong. The boundary conditions for the conformal compactification with gravity was too strong, and I think and that was very quick to do with it and made that crystal clear, and that was too strong, and that thinking about things in those terms caused us to miss a lot of interesting physics.